Hello everyone. In the last class, we talked about single-phase transformers under load operations, physical conditions, and basic equations. But at the same time, we raised the question, when the transformation ratio K is large, the primary side of the transformer and the secondary side voltage differ greatly, making it difficult to analyze the operating characteristics and draw the phasor diagram, increasing the difficulty. Is there any method to solve this? Today, let's look at single-phase transformers on the load operation, phasor diagram, and equivalent circuits, also known as equivalent circuits. Equivalent circuits are an important method for analyzing transformers. In transformers, because the transformation ratio K is not equal to 1, E1 is not equal to E2, making it impossible to form a complete circuit. Calculations become quite complex. To resolve this contradiction, winding transformation is introduced. The primary and secondary sides of the transformer have no direct electrical connection, only magnetic connection. The load on the secondary side affects the primary side through magnetic force. Therefore, as long as the magnetic force on the secondary side remains unchanged, the physical quantities on the primary side do not change. This provides a basis for transformation. To overcome this difficulty, a hypothetical winding is often used to replace one of the windings, making it a transformer with a transformation ratio K equals to 1. In this way, the primary side and the secondary side windings can be connected into an equivalent circuit, thus greatly simplifying the analysis and calculation of the transformers. This method is called winding transformation. The transformed quantities are marked with a prime symbol to distinguish them. To summarize, transformer windings transformation means transforming the secondary or primary winding with another winding to make it equivalent. At the same time, the electromagnetic quantities of the winding are transformed accordingly to maintain the unchanged electromagnetic relationship on both sides. The purpose is to use an equivalent circuit to replace the actual transformer. Principle 1 of transformation. When transforming from the secondary side to the primary side, because the secondary side affects the primary side through magnetic force balance. Therefore, as long as the magnetic force on the secondary side remains unchanged, the internal electromagnetic relationship of the transformer will not change. That is, before and after transformation, the electromagnetic relationship of the entire circuit will not change. Principle 2 of transformation. The electromagnetic relationship between the primary and secondary sides remains unchanged before and after transformation. Power loss remains unchanged. Various losses remain unchanged. Energy storage in the leakage magnetic field remains unchanged. The quantities of the actual windings are called actual values. The quantities of the hypothetical windings are called transferred values. Maintaining the magnetic force of the secondary winding during transformation is called secondary side to primary side transformation. That is, transforming the secondary side to the primary side. Maintaining the magnetic force of the primary winding during transformation is called primary side to secondary side transformation. Here, we mainly talk about the quantities on the secondary side. The transformation method is as follows. First, the transformed value of the secondary current. The principle of transformation is that the magnetic force produced by the secondary side remains unchanged. I2 prime equals to N2 divided by N1 times I2 equals to I2 divided by K. Second, the transformed value of the secondary electromotive force. Because before and after transformation, the main magnetic flux and the leakage flux do not change. According to the proportional relationship between electromotive force and turns, E2 prime equals to K times E2 equals to E1. The same applies to voltage. U2 prime equals to K times U2. Third, the transferred value of impedance. The principle of unchanged power before and after transformation. R2 prime equals to the square of K times R2. X2 prime equals to R2 prime equals to the square of K times R2. Z2 prime equals to the square of K times Z2. Transformation is just a mathematical method. It does not change the electromagnetic relationship before and after transformation. That is, before and after transformation, the magnetic force balance relationship, power transfer, and laws should remain unchanged. All physical quantities in volts, such as electromotive force and voltage, the transferred value is equal to the original value multiplied by K. All physical quantities in ohms, such as resistance, reactance, and impedance, the transformed value is equal to the original value multiplied by the square of K. The transformed value of current is equal to the original value multiplied by 1 divided by K. Previously, we introduced 6 basic electromotive force balance equations. Now let's look at the situation after transformation. It is obvious that the transformation ratio K is no longer present. After class, try doing it yourself. Transforming the primary side to the secondary side. Emphasize one point. The result of transformation cannot change the physical nature of the transformer's operation. That is, it does not change the internal electromagnetic relationship of the transformer. That is, it does not change the magnetic field, does not change the magnetic force, does not change the power relationship. This is to say, before and after transformation, they are equivalent. However, after transformation, the secondary windings induce electromotive force and the primary windings induced electromotive force are equal. That is, E2 prime equals to E1. Then the previously separated equivalent circuits can be unified. According to the transformed equations, we can create the equivalent circuit of the transformer. The formation process of the T-type equivalent circuit is shown in the diagram. The T-type circuit contains series and parallel circuits, complex calculations with complex numbers. In actual transformers, I1 is bigger than I0, Z0 is bigger than Z1. I1, Z1 is very small. When the load changes, the change is small. Therefore, assume Im, Zm does not change with the load, then move the excitation branch from the T-type equivalent circuit and parallel it at the power port to obtain the T-type equivalent circuit. Simplified equivalent circuit. Under load operation, Im in I1n is very small. In practical engineering calculations, ignore Im. Remove the excitation circuit to obtain a simpler impedance series circuit. Rk is called the short circuit resistance. Xk is called the short circuit reactance. Zk is the short circuit impedance. Emphasize one point. Under no-load operation, the simplified equivalent circuit cannot be used. From the simplified equivalent circuit, we know that the short circuit impedance limits the short circuit current. Since the short circuit impedance value is very small, the transformer's short circuit current value is large, generally reaching 10 to 20 times the rated current. Next is the phasor diagram. We will create a simplified phasor diagram. Steps to draw the phasor diagram. Assume the transformer has an inductive load corresponding to the simplified equivalent circuit. The voltage equation is U1 equals to I1 times left bracket RK plus J times XK right bracket minus U2 prime. According to the equation, a simplified Phasor diagram can be drawn. Analysis and calculation. Methods for transformer load operation include basic equations, equivalent circuits, and Phasor diagrams. Basic equations are the mathematical expressions of the electromagnetic relationship of transformers. Equivalent circuits are the analog circuits of the basic equations. Phasor diagrams are the graphical representation of the basic equations. The three are unified. For general quantitative calculations, use equivalent circuits to discuss the phase relationship between various physical quantities. Use Phasor diagrams. Basic equations are the foundation. Alright, that's all for today's class. Thank you for watching.